everyone, welcome back. In the last video we have done about the Lorentz transformations, and also we have discussed the correlation between the Galilean transformation and Lorentz transformation. Also we have discussed in what circumstances the Galilean transformations lead to the Lorentz transformations, and we have also discussed the postulates of spatial theory of relativity given by the Einstein, and we have used the two postulates of spatial theory of relativity in order to derive the Lorentz transformations. Okay, so let us sum up the both postulates of spatial theory of relativity. The first postulate tells about the covariances of all the physical laws, which simply, in the brief, we are discussing in the brief, not in details. In the simply, the first postulates tells about all the physical laws and events are simply exactly same for all kinds of frame of references. It doesn't matter the frame of reference or an observer is moving with some kind of velocity. All the physical laws and phenomena are happen with the same nature. Okay, so this is the covariances of physical laws in all kind of frame of references. And the second postulate given by the Einstein for spatial theory of relativity is that it tells about the constancy of speed of light, which simply means that the speed of light doesn't change in order to observing by different kinds of observers placing in different kind of frame of references. In short, whether the frame of reference is moving with some kind of velocity and you are staying in that particular kind of frame of reference and you are observing some kind of phenomena related to speed of light, then the speed of light observed by you will not be affected as that of the speed of light observed by the another kind of observer. Simply, the speed of light in all kind of frame of references is constant, having the value 3 times 10 to the power 8 meter per second. Okay, now in this video we are going to discuss the application of spatial theory of relativity, the length contraction. Okay, so our topic is length contraction. So this is our topic of this video. So in order to do that, let us consider two frame of references, S and S dash. This is S frame of reference and another frame of reference is S dash. Okay, so the coordinates axes are OX, x-axis, OY, y-axis, and OZ, z-axis of S frame of reference, and this is the another frame of reference S dash, which is moving with velocity v in positive x-axis, and this is a x dash axis, this is a OY z dash axis, this is a OY dash axis. Let's say this is the O dash here, and this frame reference is moving with velocity v. Okay, with respect to this frame reference S. Now let us consider, we have to consider length. So let us consider a simple stick or an object having some actual length. So let us say in the frame reference S dash there is an object having length some, let's say this is let's say L naught here. It's the proper length is L naught, actual length is L naught, let's say 1 meter, 2 meter or 1.5 meter, anything. Okay, right. Now the coordinates, this object is laying on the x-axis towards the x-axis, so L naught is along the O dash x dash axis. So the coordinates of ends, this is one end, this is the another end of this stick. Okay, so the coordinates of ends of these sticks observed from this frame of references will be like this will be x1 dash here, and this will be x2 dash. So x2 dash is the distance of this end from the origin, and x1 dash is the distance from this end to the origin. Okay, again there is an observer in S frame which is also observing the length of this stick, but in the S frame. So he will appear the different kinds of coordinates of the ends of this stick, because this frame of reference is moving with velocity v in the comparison of S. So the coordinates will be changed. They will not be x1 dash and x2 dash. They will be something else. Okay, so let's say the coordinates of first end of this stick having the proper length L0 or L0 are x1, from this origin, and the second end of this stick is situated as at x2 according to an observer which is in S frame of reference. Okay, so this is what we have, the mathematical or demonstration interpretation of this phenomenon. Okay, now you can look at here that let's say the length observed by an observer O in S frame reference, length of a stick observed by O in S frame of reference. Remember, we are discussing about S frame of reference. That will be, let's say, L, and L will be, if I subtract x1 from x2, I will get this one value, or this one will be equal to the length. Okay, so x2 minus x1 fraction, x2 minus x1 length will be the proper length of this stick observed from S frame of reference. So that will be x2 minus x1. Let's say this equation is 1. Okay, now if I talk about the length observed by O dash observer of this same stick, which is placing in S dash frame of reference, and it is also moving, the L0 proper length of this stick is at rest in S dash frame of reference, which is completely moving with respect to S with velocity v. Okay, so L0 according to an observer O dash will be, it will be x2 dash minus x1 dash. If I subtract x1 dash from x2 dash, I will get this value. This is the L0. Okay, so this will be x2 dash minus x1 dash. This is equation number 2. Right, now let's say the velocity of this frame reference is just comparable to the speed of light. Okay, because we are understanding this phenomena by taking the consideration of postulates, especially of relativity. So that's why we are considering that, we are supposing that this complete frame of reference is moving with some kind of velocity which is comparable to the speed of light. So in order to do that, we will use the Lorentz transformation. We will not use the Gaussian transformation in this particular kind of case. Okay, so Lorentz transformation, using Lorentz transformation here, the Lorentz transformations for the distance are x2 dash will be equal x2 minus what? This will be Vt divided by under root 1 minus v square upon c square. Here v is the velocity of frame of reference S dash, in which x2 dash are the coordinates of another end of the stick. Okay, and t is that particular time at which this phenomena is observing, and c is the speed of light here. Okay, and x1 dash will be in the same nature, x1 minus vt upon under root 1 minus b square upon c square. Correct. I can put x2 dash and x1 dash from these two factors in equation number 2. Okay, so L naught will be, this will be x2 dash minus x1 dash. Now I am going to subtract x1 dash from x2 dash here. So let me write that x2 minus vt upon under root 1 minus v square upon c square, and minus, I have put the value of x2 dash here from this factor. Now minus x1 dash is this one, this is x1 minus vt upon under root 1 minus v square upon c square. Correct? Now the denominator is same, it can be taken as common. So this is 1 upon under root 1 minus v square upon c square, and in the bracket x2 minus vt and minus x1, and minus will become positive. Okay, now this complete factor is cancelled by this plus factor. Now the rest is x2 minus x1 here. So this is, let me write down it as here. This is going to equal L naught. The rest terms are x2 minus x1 divided by under root 1 minus v square upon c square. Right? Now in equation number 1 you can easily see that this x2 minus x1 is mathematically equals to the L. So using equation 1, L naught equals L divided by under root 1 minus b square upon c square. Okay, now this is the final factor what we have to discuss here. Now what about the L naught and what about the L as well? Now L naught is the actual length of that stick which was placed in the S dash frame of reference, which was moving with velocity v in x direction with respect to s. Correct? So L naught here is said to be as the proper length, proper or actual length, right? And L was the length observed by an observer O placing in S frame of reference, which was at rest in the comparison of S dash, which was moving with velocity b with respect to s. So L naught was improper length, because this was observed, this was measured by an observer which was at rest in the comparison of simply S dash. Okay, so now the relation between L naught and L is taken out to S. Now mathematically you can see here this factor, this is 1 minus v square over c square. Okay, now if the velocity of the S dash frame of reference v is very small, let's take an example. So if this value is very small, then it will be divided by c, so it will become more small, okay, and its square will become more small, and this complete factor will be subtracted from 1. So this complete factor will be very less. Okay, so this complete factor will be very less. It simply means that the L naught here, this is complete factor very less, and when the less value, when we divide something by very less value, then that will become greater. Okay, this is a simple basic rule of algebra. So it means that this complete value will be what? Greater. This complete value will be greater by 1. So L naught will be greater by L here. Vice versa, you can put the value of L in equals to the L naught here. L equals L naught times of under root 1 minus v square upon c square. Right? I have multiplied this factor with the L naught. Now let's understand by this way. here this 1 minus b square upon c square, this complete factor is very less. Okay, this factor will be less y1 because something is subtracting from 1, so this will become the less y1, this will be smaller than 1, okay, in the simple way. So whenever we will multiply the actual length L0 with a smaller quantity, smaller than the 1, so this will become very less, this will become less value. It's mean that L is less in the comparison of L0. So what we have here, so in this way we have obtained L is less than L0. In the same way, this complete L0 is very greater than L. It simply means that when we look the length, the proper length of the any stick or any object from rest kind of frame of reference, then it appears as contracted, as less. It's mean that if this marker is placing in such kind of frame of reference which is moving with velocity v in the comparison of some rest frame of reference, okay, then and if I am observing the length of this marker which is in the another frame of reference which is moving with velocity v and I am at rest, then I will appear its length as contracted. Let's say its length is approximately 6 inches or let's say 12 centimeter, okay. So this 12 centimeter which is proper length L0, okay, will appear to me as contracted approximately 11 centimeter something or 10 centimeter something, and it will be depend upon the velocity of the frame of reference by which velocity this marker is moving, okay. So this is the length contraction and formed by the using the considerations of Lorentz transformation, okay. So this is done. Now let's talk about the time dilation by using the Lorentz transformation here. So next topic is time dilation. This topic is also pervaded with another name like watches are appeared slow, okay. This is something like that, watches are appeared slow in moving, okay. So again let us again consider two kind of frame references in which one is at rest. This is y-axis, this is z-axis, this is x-axis, and observer is here. Oh, this frame reference is S, and another frame reference S dash which is moving with velocity v in the comparison of S, and this is a z dash axis, this is the x dash axis, this is the y dash axis. And again in the last article we have considered a stick, now we are considered a watch here in the frame reference S dash, correct. Now let's say this is the watch which is making some sounds, okay, like tick tick, okay. Now there is an observer O dash which is observing the sounds formed by this watch, okay. Now let's say one sound from this watch is heard by this observer O dash at some kind of time of instance of time, let t1 dash. So t1 dash is the time at which an observer O dash hears the tick sound of the watch, okay. And let's say just after this one tick sound the observer O dash hears and the tick sounds just after the one tick, okay, and that will be what at let's say at t2 dash instant of time, okay. Now the difference between these two tick sounds will be t2 dash minus t1 dash, right. So the difference between tick sound will be delta t dash. This will be t2 dash minus t1 dash, right? Again, the same tick sounds at the same instant, okay? At the same instant, when these two tick sounds are heard by another observer O in frame of reference S, which is at rest. Again, just mind that this frame of reference S dash is moving with velocity v, as well as this watch is also moving with velocity v because it is at rest in the frame of reference S dash here, okay? Again, let's come back to the topic. The two tick sounds which are observed, which are heard at time t1 dash and t2 dash respectively, alternatively by this observer O dash, when these two tick sounds are heard by another observer O here, then the time difference between two tick sounds heard by an observer O in the frame of reference S will be, that will be difference time, this is time difference here. So time difference between two ticks sound from, or sorry, in frame of reference S, this was about S dash, that will be delta t, and that will be, let's say the first tick sound is heard by this observer at t1 dash and another is at t2 only, oh sorry, t1 and t2 respectively. First sound of tick is heard by this observer O at time t1 instant, and another tick, alternatively another tick sound is heard at time instant t2. Let's, this equation is 1, this equation is 2. Now, in order to relate both the equations or time differences between frame of reference S dash and S, we will use the Gaussian transformation, and we will not use a simple Lorentz transformation. We will not use a simple Lorentz transformation here. We will use here inverse Lorentz transformation because time cannot be negative. Let me make you understand how. Lorentz transformation are simply x dash equal x minus vt upon under root 1 minus v square upon c square, correct? And about t dash, it is equals t minus vx upon c square and divided by under root 1 minus v square upon c square. These are the simple Lorentz transformations, okay? In order to relate equation 1, equation 2, or the difference between times of or hearing sounds from S dash and S references, we will use the inverse Lorentz transformations, not these transformations, okay? Because time cannot be negative, okay? That there will be a difficult into solving the algebraic problem of this interpretation. So we will use the inverse transformation, because in this equation time can in the simple ways time cannot be negative, so velocity of this watch or the sound cannot be taken as negative, so we will use here only the Lorentz transformation inverse form, so that will be plus here, that will be plus here, okay? So if you want to convert the Lorentz transformation into its inverse form, so again, so simply you had to replace this v by minus v here, okay? So I can put this transformation here in the equation number 1. There is no role of distance here, so I am removing this one. So by making this equation in the use of 1, the delta t dash will be, this will be t2 dash here, this will be t2 plus vx upon c square divided by under root 1 minus b square upon c square, and minus t1 dash, this will be t1 plus vx upon c square upon under root 1 minus b square upon c square, okay? Again, this factor is common in the denominator, so it can be taken out. So this will be 1 upon under root 1 minus b square upon c square in the bracket this will be t2 plus vx upon c square minus t1, and this will be minus plus minus bx upon c square. This quotient is cancelled by this quotient. The rest term is t2 minus t1. Okay, this t2 minus t1 is going to equal from this equation 2 as delta t. So this will be t2 minus t1 divided by under root 1 minus v square upon c square, or this will be delta t divided by under root 1 minus v square upon c square here. This is going to equal what? Delta t dash. So delta t dash, what we have obtained up till now is this one value. This is delta t dash equal delta t and divide by under root 1 minus b square upon c square. So this is what we have, the expression for time dilation. Now let me make this equation in this form also. Delta t, I am making this equation equals to delta t. Delta t equals delta t dash multiplied with under root 1 minus v square upon c square. This is another form of this equation. Okay. Now let us understand the physical meaning of these two equations here. Delta t dash is nothing but the time difference between the sounds of two ticks observed or heard from S dash frame of reference by O dash observer. Okay, and delta t is the same time difference between these two tick sounds observed from S dash frame of reference by O observer. Okay, and the relation between these two time differences is delta t dash equal delta t upon this factor under root 1 minus b square upon c square. Now by mathematically you can see here this complete factor is again lesser by 1. Okay, so this factor is lesser by 1, and when delta t will be divided by lesser than 1 value, it will be greater. Okay, so here this complete value will be greater, or delta t, and the relation between delta t and delta t dash will be like this, because this complete factor will be greater by 1. Again from this equation you can see here this complete factor will be lesser by 1 because velocity of this frame of reference will be lesser than the speed of light, and when we divide that particular square of that velocity by the square of the velocity of light, this will be very lesser, and the lesser quantity will be subtracted by 1, so this will become again lesser than 1. So whenever delta t will be multiplied by the lesser than 1 value, it will be lesser. Okay, so delta t will be lesser in the comparison of delta t dash. Sorry, delta t dash will be lesser. Delta t will be lesser here because this complete factor is lesser than 1. So delta t will be lesser in the comparison of delta t dash here. So by both equations you can take one meaning. So the time difference observed from S dash frame of reference is lesser than the time difference observed by the frame of reference S dash. It's mean that if the two ticks of sounds are heard after an interval of 1 second from S dash frame of reference by this observer O dash, it's mean that if I am standing in this frame of reference S dash and I am observing that the two ticks of sounds are heard by a time difference of 1 second, then at the same time another observer which is standing in the S frame of reference will hear the time difference between these two same tick sounds in the lesser time. it will not hear the time difference as 1 second. It will hear the 2 ticks at after some 2 seconds, after some 3 seconds. So the time differences will be greater for that particular observer. It's mean that it will observe the slowness of the watch, that it will hear, it will observe, it will say that this watch is moving slow, it is showing the time very slow. Okay, because after some time it will observe, it will hear the 2 ticks time differences. Okay, so this is all about the time dilation and length contraction. So I think this is enough for this video. Let's meet in the next video. In the next video we will discuss about the addition nature or additivity of the velocities. Okay, also in the later videos we will discuss about the covariances or invariances in the Lorentz transformation. We will discuss about the invariance in the physical laws or physical equations like wave equation, okay, by using the Lorentz transformations. Okay, so thanks for watching. Let's meet in the next video.